Hello, welcome to CS101, Introduction to Computer Science. This is class 10 and we'll be talking about databases and big data in this class. So what is a database, or what are DBMSs or DBs, right? A database is an organized collection of data which is comprised of schemas, tables, queries, reports, views, and other objects. So that's the formal definition. But the basic idea is that it's a computer software application that interacts with the user and other applications and the database itself to capture and analyze data. So there's a few examples that if you ever end up in this field, MySQL, PostgreSQL, Oracle, SQL Server. The idea is that these are software. Database is basically a software that holds data that can be easily queryable and can be analyzed pretty fast, right? So that's what a database is. So you could store things in the file system. But storing data, structured data in a database is just much easier because it lets you query and get the data faster. So why do we need databases, right? So let's consider a website. So you've built a website in HTML, CSS, JavaScript, so a user can see it. Now, you can't just build a front end, you need to build a back end as well, as we found out in the previous class. Then you build this in PHP and Python or Java or Ruby. Right, kind of blended Java and Ruby there, sorry about that, but Java or Ruby. So the idea is that you have a front end, but that alone isn't enough, so you pull in data from the back end. But where does this back end store data? Does it store it in files? Sure, it could. You know, it could also store it in memory and things like that. But typically, the back end application stores the data in databases. It could be a SQL database or a relational database. These are the traditional type of databases used, and now there's this emerging trend of NoSQL or non-relational databases that are used in big data. So we'll talk about those two in a little bit, but the idea is that, you know, any front-end facing application, it need not be a website, it could be a mobile app or other software applications really, eventually store data in a database somewhere. And obviously there are exceptions to this, like for video editing software, or like for example Photoshop imaging editing software. You don't necessarily need to store data in a database. You can just save files to disk, etc. But most online services that deal with data and a lot of data store data in databases. So when people talk about databases, they usually refer to relational databases. That's, you know, the traditional definition of a database for many decades now. So these relational databases have tables which contain data, and these are related to other tables that hold other related data. We'll see some examples in a few seconds. And you can set up indexes on these fields, and that allows you to do quick searches on those fields. So databases are good for storing data, retrieving data, doing queries, and they're basically set up to do this. So you don't need to in the software actually worry about this, because databases do that for you. So these have been around for 30 plus years, right, which is a long time in the computer industry. Oracle, for example, has been around since the late 1970s. And there's quite a few examples of relational databases or SQL databases. There's the commercial vendors like Oracle, Sybase, Microsoft SQL Server, which is also very popular. These are commercial. There's free and open source databases like MySQL and PostgreSQL as well. So you'll find a lot of these like Microsoft SQL, as well as more recently MySQL and PostgreSQL, which are used in a lot of websites as well. There's also emerging trend for non-relational databases, which are also called NoSQL databases. So these are kind of the new kids on the block. They came about 10, 15 years back, and they're related to the rise of big data and the rise of internet giants like Google and Facebook. And the reason they came about was because relational databases weren't enough for internet scale. You have billions of users generating millions of events each, and hence you have billions or trillions of events you need to save, and relational databases couldn't scale to those sizes. So you have a whole bunch of new databases such as MongoDB, HBase, Cassandra, Elasticsearch, and DynamoDB, which is a cloud-based database. We'll talk about that in a later class. So these are kind of NoSQL non-relational databases which have come about for handling big data. We won't discuss NoSQL databases in this course, but you know, if you ever get into big data, you might probably use one or the other. Let's just quickly go over an example of how SQL and NoSQL databases differ, not so much from how they're implemented, but how you would use them, right? So relational databases typically use SQL as the query language, and non-relational databases don't. They usually use some other object-oriented programming as the query languages, though some non-relational databases, NoSQL databases, are beginning to use SQL-like queries on top. So this example here shows you the difference between SQL statements on the left and NoSQL database like MongoDB on the right. So if you look at the left column, you see a whole bunch of select statements. So the first statement is select star from users. What this means is give me the entire list of users from the users table. The second one is select ID, user ID, status from users. So you're just getting the ID, user ID, status, only those fields from users. So users table could contain a lot of attributes like birthday, age, and things like that. So we don't want that. The third one is interesting because you say select star from users where status is equal to A. So you have a status field and you want to select a user where their status is a particular status. So this is where databases begin to shine. Rather than try to build this sort of functionality in your own software, you simply store data in a database, and when you do a query like this, databases can get you the answer very efficiently. You don't need to worry about building that logic into your code. If you skip step the line 4 and go into line 5, where user ID like percentage, so you can do things like fuzzy matching, where you don't need to know the exact string or the exact number, but you can kind of find something that looks like it. And then the second to last line where you have where status is A, order by, so you can get or list of users where their status is A, but you can also order the results and things like that. Now on the right side, on the right column, you see the exact same queries actually on a no relational database like MongoDB. So db.users.find, find and then get just the fields user ID and status, and then you find where status is equal to A, and those sort of things. So you can see that you can do the same sort of queries in a relational database and in a no relational database. But while relational databases you query in SQL, with non-relational databases you use some other object-oriented programming model. Here's a more complicated example. We're not actually going to go into detail on this, but you can see how one thing maps to the other. But the idea is that complex data can be queried using SQL statements in a relational database. And complex data can also be queried in NoSQL, but these are done using programming constructs rather than SQL, which is set-based language. So some people call SQL a set-based language because it gives you sets as data. When you do queries, you get sets. And with NoSQL, you basically do it in the programming model. You use a programming language to query the data. And here's a very simple sort of relational SQL data model. So just to give you an example, so let's say we have a database that needs to store courses and instructors. The idea is that you have three what are known as tables, right? And you see on this example on the right, you have an instructor table, a course instructor, and a course table. So the idea is that the instructor table will have a list of all instructors. For example, it would have my name in it. And there's a course table which would have a list of all the courses. And the idea is that one course could have more than one instructor, and vice versa. One instructor could be teaching more than one course. So this model here lets you link the instructor and courses table using another external table called course instructor. So the database is actually a collection of relations. So it's a collection of multiple tables that you see in this image. A relation has a set of attributes. So each table, as you can see here, has a set of columns that are used to store the data. And this column, which is also an attribute, it has like a type. So there's ID, last name, first name, hire date. These are columns or attributes. A relationship table actually stores a set of tuples, rows basically. So for example, in the instructor table, it would have my name in it, Spencer Samuel, and a hire date, 2017. So that would be one row in the database table. So you can see that this example here, it's the entire image is a database, and the database has three tables, and each of those tables has multiple columns, and you don't see the rows in here. But if you did a select star from each of these tables, you would see the rows, which is the actual data set up in these tables. And you can see there's a course instructor table which joins the two. right? So that's kind of, there's a relationship between these tables there. Okay, so let's talk a little bit about distributed systems and big data without going into too much detail. There's many complicated distributed systems which are especially used for big data processing. There's a NoSQL or non-relational databases we talked about. There's distributed compute, Hadoop. There's orchestration software. Zookeeper is an example, and deployment tools like Docker. So the reason I'm bringing these up is that if you go beyond simply, queries and databases, and you want to look at things at scale, you will often use some of these tools, right? Whether it be for deploying software or for maintaining servers or for orchestrating or for processing large volumes of data. Just to give an example, let's just talk very quickly about Hadoop, which is a trendy sort of big data software. There's many alternatives to this, but Hadoop has captured the imagination of a generation of data scientists. So let's just talk about this very quickly. You need to process a large volume of data, right? Like say terabytes of data or even petabytes of data. So how would you go about it? Would you want to process this all on one very, very large computer, or would you distribute the workload across hundreds or thousands of smaller computers? And the answer is almost always the second one. You would want to distribute this giant task across hundreds or thousands of smaller computers, because what can happen is that the work can be parallelized, and it helps to parallelize compute, memory, and hard disk resources. So you're not tied to, growing one computer bigger and bigger to handle more volumes of data, but rather you distribute it across a whole bunch of machines, and those can more effectively process that data. So Hadoop basically does this, right? So Hadoop, if you've heard about it, it's a distributed processing engine, distributed compute. The idea is that you submit a job to it, it distributes it to your cluster, your data center, and processes the data and gives you back the result set that you need. So you still need to write a program, a Hadoop program, to actually process the data. But Hadoop is a what they call a MapReduce framework that lets you do distributed compute to process large amounts of data across data centers and take advantage of parallelization. And that brings us to the last topic in this class, which is big data. The idea is, it's very simple, right? Like it's a trendy word going around, but the idea is that you collect data from various sources, could be anywhere. You send it through messaging or other streaming software such as Kafka or Flume. These are processed in batch or real time using Hadoop, which we just saw, or Spark or Storm. These are stored in large databases such as SQL or NoSQL databases, and they're typically built by data engineers and analyzed by data scientists. So there's a whole bunch of software that forms this big data stack or big data ecosystem, and the idea is that you use one or more of these components to actually build these systems. So that brings us to the end of this class, which is about databases and big data, and hopefully that helped you understand